Okay, and we're back. Bless you.
Thank you.
Oh, you're in person?
Yeah.
Nice to see you.
You too. Lovely.
I wish we were doing something more. Don't freeze up on me. I'll be in terrible shape here. All right, so you recall what we were doing before we were rudely interrupted by my not having the power cord for this. We were having, we're getting there. We were starting the neurotransmitters, and this is basically where we had left it off. Was to understand that this is the basic categories. And it's amazing to me physiologically how something like a relatively simple component like an amine could have so much impact on us, but it does. So again, tyrosine is able to, with some limited substitutions, create a dopamine, norepinephrine, and epinephrine. And the indolamines, okay, as I was saying before, we have effectively the breakdown product becomes indole, and I can't speak to the biochemistry of it at this point in time. It's been a long time since I did biochem. Serotonin utilizes tryptophan, and histamine utilizes histidine. These are both very, very powerful substances, and they're not exclusively neurotransmitters, would be the way I would frame it. We're going to see applications of serotonin and of histamine in a variety of other systems that are there. You're going to see histamine with regard to white blood cells. You're going to see histamine with regard to gastrointestinal physiology. You'll see serotonin with regard to that. You'll even see, I think, serotonin utilized with blood clotting. So these agents, depending on where they're located, most time our context for histamine is antihistamines that we take for allergies, right? So whether you're taking a Zyrtec or you're taking the old style ones, which are like Benadryl or chlorpheniramine, there are so many different ones that were in this category. And when we get to that, we start looking at those agents vis-a-vis immunology and allergy. Basically the distinction between those kinds. Again, the antihistamines are more about blocking certain kinds of histamine receptors than anything else. So, that's where those agents come from, and those histamines function interestingly, as we'll see too. So, as you can see, there's a lot of things that they do, and we're particularly going to see those in the autonomic nervous system. Other than acetylcholine, the autonomic nervous system uses a lot of norepinephrine, a lot, because that's the primary component that sympathetic nerves produce. Indirectly, the sympathetic nerves, by way of what's called the adrenal medulla, which is really almost like an end organ of part of the sympathetic nervous system, utilize both norepinephrine and epinephrine. When you hear about, and again, the old terminology was noradrenaline and adrenaline. Now we use the term epinephrine. And for years, they have known that imbalances in these were associated with mental illness. It was just the way they went about going after them. And unfortunately, for any extent, when you have a fair amount of exposure to these by way of my kids, particularly my two younger kids, with some interesting needs to having been at least at one time when they were younger on those medications. There are more stories to come. It's like you're living my life. So I keep telling you, don't have kids. Oh, you're terrible. Don't even start. Don't even start. Amino acids in and of themselves play a really important role. You're already familiar with the top three of these from biochemistry, or you will be from glutamic acid, aspartic acid, and glycine. Very, very familiar names. GABA might be the one that you don't know about or know the least about, but it's tremendously, tremendously important in this context and its utilization in the central nervous system. GABA is, we always just say GABA because it's a lot easier than saying gamma aminobutyric acid. So It's difficult to prove which are neurotransmitters, but we know these. In general, glutamate and aspartate are excitatory, not always, but nearly always, with some exceptions, and glycine and GABA are typically inhibitory. That much I can tell you. So you want to paint with a broad brush, which is never a good idea when you're dealing with biochemistry, and particularly so that's another area. These are also interesting, and these having to do with what are called neuropeptides. So they're typically short chains of amino acids, maybe 8 or 9 amino acids, typically. Very diverse functions. Substance P. We don't even give it a name at this point in time. We know it has a certain association with pain signals. You might remember when we were doing joints in the anatomy, we talked about capsaicin, which is the extract of red pepper. Okay, so capsaicin, which is derived from what are called capsicums, typical bell peppers, well, whatever shapes and sizes are in the family of capsicums. And the veins and seeds contain varying degrees of capsaicin. The hotter the pepper, the more capsaicin. So if you're like me, my motto: if you're not sweating, you're not eating. So you got kick it up a notch.
So you're saying live dangerously while eating?
Well, hey, well, it depends if you're up to it. I mean, sometimes your stomach goes, nah, enough. Had enough of that type of stuff. But I personally prefer a little kick me up. It's like my wife made cornbread, and all of a sudden I'm eating it. I'm going, it's got some kick. She goes, red pepper flake. So you kick this up. Yeah, baby. Nevertheless, what capsaicin is thought to act when you use it topically is to deplete substance P. Okay, so it's not clearly understood, and it doesn't work for everybody. It works about a third of the time. A third of the people can't tolerate it, and a third of people has no effect generally with that type of thing. There's another thing that people erroneously think works the same way, and it's called a TENS unit. Did anybody ever hear of a TENS unit? Because you probably in sport you would have heard about it. It stands short for transcutaneous electrical nerve stimulation. And what it is used sometimes is for areas of pain to apply that. It acts like we call it a gating mechanism. So think of it as like jamming radar. So you're producing an electrical signal very low that you can modify based on its amplitude or frequency. And you can utilize that to basically, so your brain doesn't interpret it as pain. And we did a lot. We were around when it started. I was still a student, and some of my colleagues in the early years were using that alternatively to pain medications. It's a very good thing, but not necessarily the same thing. It's interesting. You can now buy those. You can go on Amazon and buy one if you want a TENS unit. We get to endorphins, which is short for endogenous morphine compounds. So they are similar or analogous to morphine, but they're produced endogenously. And so they have a variety of roles and a variety of names. And the way those compounds all work is to produce the perception of pain. There's no danger associated with them. And so, and they've been attributed to a lot of things, like these gut-brain peptides. Gut-brain peptides, there are a certain amount of endorphins that are produced that act similarly to those. The gut-brain peptides regulate digestion, and we'll look at the roles of somatostatin and cholecystokinin, which are produced to some extent by food entering the small intestine. But the gut-brain peptides themselves act, some of them that are not mentioned here are more in the category of endorphins. And so there's a certain amount of pleasure that people just get from eating attributed to that. Or with sports participation, a lot of people get, it's almost like a breakthrough moment. Like here, for years, when the running craze started back in the late 60s, you heard about the runner's high. And so they found that wasn't just exclusive to running, but various kinds of physical activity produced a certain amount of this as well. And so that's just part of that particular thing. And then interestingly, these are quite interesting purines. So purines, again, adenine and guanine based substances, in particular adenosine is the best known of that, and the action of caffeine, which blocks adenosine receptors. And what it basically, adenosine is something, as you can see, have an effect in both the central and peripheral nervous system. So the ATP in and of itself still plays a role as a neurotransmitter, and typically it's inhibitory. And so when we block it, such as what we do with caffeine, we tend to, it effectively becomes a stimulant, if you want to look at it that way. And it's not just something that wakes you up like having one of these, like an energy drink or getting something at a convenience store where you're on a long drive, okay? Because it will stimulate a variety of things. So caffeines will stimulate, digestive activity, urine production, that type of stuff. Will also be stimulant like that. So as you can see, calcium influx in astrocytes is at least one of the mechanisms that they talk about. And then you get to these, and here's the other one we talked about, nitric oxide. Here, interestingly, playing a role, not necessarily well defined, as called gasotransmitter, as well as carbon monoxide. So carbon monoxide is a toxin. Hydrogen sulfide is a toxin. Okay, nitric oxide is a chemical that's a potent vasodilator, at least when it's released in blood vessels, but it has some interesting, all have interesting effects in very tiny amounts with G protein receptors in the brain. They're lipid soluble. So we're looking at nitric oxide a lot now as we begin to understand its role in learning and memories, brain damage, smooth muscle relaxation, you could understand because of its dilating effects. So, I mean, there's a lot to it when people who study this say in neurology and in research aspects of it. So I think it's well worth looking at. And nowadays, it's a more germane topic with the legalization of cannabinol-based products. Very interesting molecule, tetrahydrocannabinol, which is the active ingredient in marijuana most people are very aware of. Okay, it is typically associated with G protein receptors. It is lipid soluble, synthesized on demand. So we make those substances. So you can certainly consume them. And nowadays there's so much about with the legalization, whether it's for medical usage or for any usage, depending on what the state governments are for. Okay, it's fascinating. Okay, is what they're doing is they fractionated it, as most of you would probably be aware of, into different components, some of which are more have more of the quote unquote drug like effect, we call it a euphoric effect, and others where it is more for enhancing the ability of certain pain medicines, anti-nausea agents, appetite stimulants, which were always kind of what we saw in the early days of marijuana. Those were the things it was consistently doing: appetite stimulation, sort of augmenting various kinds of pain medications, and certainly, and perhaps most importantly, was its ability to be an antiemetic, to really limit nausea and vomiting, particularly in patients who were getting nasty things, like cancer chemotherapy agents, which had a lot of side effects. Like for 15 years, I didn't throw up. Just saying. And I didn't treat any patients when I was doing it. That would be wrong. Just saying. It's funny, once I got my doctorate, I stopped doing it. I couldn't justify being under the influence, working on somebody or making a medical decision. All of a sudden it just clicked. Said, can't do this type of stuff. But all that being aside, what's interesting about it is the lipid solubility, the fact that we make an agent, the THC molecule, when it breaks down, let's say it's derived from marijuana ingestion or smoking or however one takes it in, has about a multitude. You know, I've heard several authors say that it's got about 100 different breakdown products that, depending on how it's metabolized, it can have a lot of impact. So what we hear about, the THCs and that type of stuff. So we know that it does play a role, and but the nausea, appetite, and really as an augmentation for pain has been very, very useful with regard to that. So we look at them and we group them into the effects and their actions. That's the next part of this. So again, it's all excitatory versus inhibitory. There's really no middle ground as to what it does for the most part. There are a few that have, unusual effects, and every so often you'll see, different things sort of novel or unusual effects that occur rarely. But anybody who's going into a medical field, or anybody, it shouldn't surprise you when you take a medication or are exposed to any substance for whatever reason, it doesn't always work the way it's supposed to. Maybe that's the best way to summarize that and to say it like that. So, the effect determined, obviously, if we want to look at it scientifically, by receptors. GABA and glycine, inhibitory, and most of the time, chloride gated channels. Alcohol, that's the effect that it has. It works on GABA receptors, the category of what are called sedative hypnotics. So all of those agents that were quote unquote tranquilizers in small doses that are sedatives, hypnotic means to induce sleep. So they are the classic category. Years ago, the category was barbiturates, which had a greater amount of addictive potential than the category that's used today, which are called benzodiazepines. And that's where Valium and more commonly today we see Ativan and Xanax and similar things, because they're a little bit safer. And again, it has a lot to do pharmacologically with their duration and their side effects. For years, they used a lot of Valium. And I remember having a pharmacist call me when I prescribed this for an elderly patient who was having muscle spasms, and we're using it to augment pain. Certainly wasn't going to be driving a car. And a guy goes, "Hey, we really don't want to prescribe this because of her age." And if you're in a field where, if you're a provider or a prescriber, here's the word: listen to what the other professionals have to say. Because I learned something, that the half-life was so long that there was a real concern, even if they got up and operated a sewing machine, or got up and were working at the stove, if your attention is not there for an elderly person, you can cause a big problem, because the half-life was quite extended. So certainly not for operating machinery or anything like that could be compromised. So the teaching point is there. A lot of people have knowledge. It's very bad to have tunnel vision and think you're the only person who knows something. Glutamate and also aspartate are usually excitatory. Acetylcholine and norepinephrine, although typically they're excitatory, they have some oddball ones. Acetylcholine is excitatory at the neuromuscular junction, and what you will see when we get into autonomic, it's classically inhibitory with regard to heart rate. That's the critical feature. Okay, so we see different things. Norepinephrine is typically excitatory, but what it does is it dilates smooth muscles in the bronchioles, and that's why it's such an effective, wide variants of that, which are called beta 2 stimulants, are what we use for asthma medications. Why, when somebody is having an asthmatic, why there's an EpiPen for someone with allergies. You're utilizing epinephrine there not to excite, but to have its distinct effect of smooth muscle relaxation in the bronchioles. So that's different. So you have to be that. And now we get to direct versus indirect. And this is important because of the speed of the response. What makes rapid responses are altering membrane potential. And as you can see, acetylcholine, sodium and potassium channels being opened and closed, amino acids, particularly those that affect those chloride-gated channels, those effects are relatively rapid. Okay? So those are direct acting. The indirect ones, by definition, take longer. And because of that, their actions are more prolonged. And so they act through second messengers and G protein related pathways, longer lasting effects, more like hormones. The biogenic amines, the neuropeptides, and the gases fall into that category. So you should remember those. When you're dealing with ion channels, it's quick. G protein, not as quick. Doesn't mean slow. No, it's not as quick. And this last category of neuromodulators, it's interesting how over time, this is where we tend to see some of the effects, or we see them only locally. So neuromodulators are an interesting subcategory of different agents that create subtle alterations. Perhaps if we think of seizure medications, it probably affects those to some extent, even though they mostly work on those ion gated channels. They probably, some of them have a neuromodulatory effect that are part of it. So I've seen that. I'm trying to think of what the other one, the category that was part of it. It'll come to me. So we've used a lot of agents whose mechanism was not necessarily unclear, whose mechanism was not terribly clear. And I'm going to have to look it up. Because when I've looked up, my wife takes Tegretol for her trigeminal neuralgia. The mechanism is not well defined, even though it's by definition it's an anti-seizure medication. But how I've looked up to see what its actual mechanism of action isn't clear. Another one that you hear a lot of people on is called gabapentin, which is known as Neurontin. Okay, and I was prescribing that and using that when it first came out, because it hasn't been around that long. We're talking maybe 30, 35 years worth of being out. And a lot of it was used a lot to deal with certain kinds of nerve pain. We were using it on diabetics with diabetic peripheral neuropathy, which we'll get to, because that's an autonomic. That's in the next chapter. So there's some ones that a lot of times when the mechanism is not clear, it probably falls in that category of neuromodulators. Okay. So again, ion channels, immediate, brief. Okay. Sodium influx contributing the most to it. Inhibitory receptors, typically, as you can see, chloride influx, leading to hyperpolarization. So all that alcohol that some of you were imbibing over the weekend, to remain nameless, at the end of the row. You were basically, the way they work, that's why we call it a disinhibitor. It's an inhibitory agent, but it inhibits channels that usually keep one's behavior under control. It's a message my daughter has never gotten. Only to excess. Just saying. Remember the corollary to that. You don't get into a fight in a pool hall.
I wasn't in one, so.
Right.
Wasn't in one, so.
Oh.
I dodged that bullet altogether.
They don't have them that much anymore.
I actually lied. There was a pool table at one place.
Yeah, they have a pool table. I spent a lot of my college years in a place in Elizabeth, New Jersey called the High Q.
Oh.
Yeah.
You a pool shark?
No, I'm terrible at it. But the guy who was who's deceased, who was on Miller Lite commercials, named Steve Miserak, who was in Cranford, New Jersey, was a middle school history teacher, was the world champion for a couple of years. And when they were doing the early days of the Miller Lite commercials, he was on it. Doing all these pool tricks. He played out of that particular place. A lot of guys, when they used to have like all the 9-ball tournaments, they were guys who all played at the High Q in Elizabeth, New Jersey. So I aspired to be that. I was terrible at it. My buddy was much better than I was. Okay. I like pool halls. I had time in between classes at school. I'd go down and have lunch at the pool hall. Go figure. G protein linked receptors, indirect and complex, obviously transmembrane changes, widespread. We're going to take a look at these different receptors when we get to autonomic. You're going to hear about what are called nicotinic and muscarinics. The nicotinics and muscarinics are different, but they're both triggered by acetylcholine. Okay, they bind. Some of those bind biogenic amines. Some bind neuropeptides. There's some very, very interesting variations that are there. And then they're just showing you that same thing we've seen all the time, the G protein linked receptor deal that you've seen, cyclic AMP, cyclic GMP, diacylglycerol, all that good stuff. The chain reaction can be ion channels, can be kinase enzymes, can phosphorylate, can activate genes, et cetera, et cetera. They use the same series of illustrations that you've all seen a lot. There's not a whole lot left of this chapter in the sense of neural integration, neurons functioning together, etc. Okay, I don't know if I can explain it to you, but it is understood from a neurological perspective how these billions of cells function into a relatively smooth operating unit. So they classify them in different pools and different kinds of zones, and you'll be happy to know you don't need to know that for me. If I don't understand it that well to explain it to you, I'm not going to. So whether it's discharge zones or facilitated zones, so for instance, so you have different zones that are there. Here's a fiber, a zone where it'll discharge, and a zone where it'll have some impact. Just for an example. Okay, a particular pathway. This is pretty common. Serial processing. This would be reflexes and basic pathways. I'm going to show you these. So you'll see it typically starts with we have a receptor, like you see something. It travels by way of a sensory neuron. It goes into our brain. We process it, and we respond to it. So you're seeing this diagram. Maybe you're thinking of something I have to write down this particular pathway, or I may make a note to look at this particular slide. Basically, that's what's going on. And a reflex is like that. You're stimulating something. It touch something that's hot. It generates a reflex, but you realize in your brain that you've touched something that's hot, and maybe it'll stimulate another type of activity. And they're just showing you that there. So at the very least, even the simplest neurological pathways always have a receptor, a sensory nerve, some kind of in-between or interneuron, and then an effector nerve going to some type of a motor nerve going to some type of an effector. That's the minimum requirements. So effectively, it's a 3-nerve circuit at a minimum. Okay, and then they describe these different kinds of parallel processing for higher functioning. You smell something, all of a sudden, you associate it, and they classify these different kinds of pathways. Whether you have one and it's got many outputs, or different kinds of circuits, or reverberating circuits and parallel circuits, and I don't care about those. It's a little too much like electricity and physics, and as we know, I don't do physics. So that's the completing nugget. I just want to introduce, and we can be done early with the autonomic nervous system. I just don't know where I put it. Hey, I put those in twice. So I think it's week 6. So I think our next year, you got the study guide I sent out, right? Here we are. Autonomic, endocrine. Some of us, we covered a little bit of endocrine in MCAT, but I'll do it for the whole group. And then the blood unit, which is fascinating. And we do a wet lab over in the zoo lab with regard to blood. And it's one of it's a particular unit I like. The blood clotting, back to the good old ABO stuff and all the things that are about that. I can regale you with stories of my 50 to 75 different units of other people's blood that I've got. Like I said, I used to be rather dull, no sense of humor, and then that whole blood transfusion thing changed it. You're not laughing. I told you that already, didn't I? A lot of other people's blood. Thank goodness. Here we go. Voila. I love this nervous system. Okay? It is my kind of place because I don't have to do anything. It does it for me. Okay? I don't have to consciously control it. Like, I don't have to worry about changing the channel on the TV set, getting food for the dog, letting the dog out, letting the dog in, letting the cat out, letting the cat in. Well, it's autonomic or automatic. What a country. It's better than like having a TV with a remote control. Are you there? There we are. So let us begin. So you've seen this, you'll see this very shortly. Smooth muscle, cardiac muscle, glands. If we just did, when you're looking at nervous systems, the autonomic nervous system does things relatively rapidly, okay, certainly more rapidly than the endocrine system. So, but it makes a lot of subtle adjustments. If there was ever a system that was the poster child for homeostasis, it is the autonomic nervous system. It is. It's taking care of you. So, and interestingly, most of the problems that you and I face health-wise as our lives progress involve the autonomic nervous system. Blood pressure, heart disease, gastrointestinal problems, respiratory problems. Most of them involve systems that we cannot control. We can control things that lead to problems. They can be absence, improper diet, a lack of exercise, smoking, a variety of toxic substances like alcohol. Just say. So, I mean, all of those things are ways that you can, your ability to impact that system comes more about quote unquote lifestyle changes that are there. Optimal support. And what it does is it basically can redirect blood to where we need it. And just our heart rate to when we need it. So it's all tied in. So I think that that's very significant with regard to there, and it operates subconsciously. So there's a lot of names for it. Since it's influencing organs, they call it the general visceral, which means organs. And it's a motor system. Even though it relies on sensory input, technically speaking, it's a motor system. So it's basically telling contract, relax, increase the heart rate, decrease the heart rate, those kinds of increase circulation, decrease circulation. So it's there. And so in the schematic that they've used forever, it's part of the motor division of the peripheral nervous system. And this is where we control it. This is where we don't control it. And it has two divisions, sympathetic and parasympathetic. And it's the easiest one to understand. You can know what one does and what the other one does with one term, right? You understand the fight or flight response. And you know what happens then. That's as close to pure sympathetic as you and I can get. So when you're threatened, when you're angry, when you're shocked about something, when that person of indecisive parentage cuts you off in the car, you nearly get into an accident. You have a few unkind things to say about it. Again, telling them to perform an anatomically impossible act of themselves or a farmer. Just say, of their choice, or the horse that brought them. Those kinds of things. That's your autonomic nervous system. What happens? Your eyes are wide open. Your circulation is pumping into your heart or your skeletal muscles. You're perspiring to cool the plant. Okay, your secretions dry up because you might have to run and chase somebody or run away from somebody. Okay, you're primed for activity. your bronchial passageways are maximally dilated. Your heart is ramped up. Your digestive and urinary and reproductive systems are basically on lockdown because you don't need them right now. Okay, that's kind of what happens. And there's a lot of other nuances that are part of that system. That's nearly pure sympathetic. The opposite is parasympathetic. So what most of you guys are when you're not hysterically laughing at my bad jokes, which I might point out that none of you are doing it today. Unhappy. Okay. Is, if Haley was here, she'd be laughing. Chelsea goes, take a day off. Oh, that's terrible. That's terrible. Okay. You're basically in full parasympathetic mode. You're sitting there. How do I know that? Because everybody's walking out to go to the bathroom, except me. And I'm the one who's had prostate surgery and 72 years old, almost. Why is that incorrect? All right, I give up. So, effectors for both. Pathways, ganglia, neurotransmitters, they have that in common. But the distinction is the structures they innervate and the fact that it's a very unique two-nerve circuit anatomically. You have a nerve that comes out of your brain or your spinal cord, and its synapses somewhere outside of the brain or the spinal cord, and then you have another nerve that goes to whatever the target is. And so where all of those synapses occur, they form, because they're outside of the central nervous system, they form what's called a ganglia. So the terminology that we use are pre and post ganglionic. The nerve that's either going from the brain or the spinal cord to the ganglia, pre-ganglionic, and the nerve that's coming from the ganglion to whatever the target organ is, whether it's close at hand or far away. It's called post-ganglionic. And the good news, every pre-ganglionic fiber releases the same neurotransmitter. Better yet, you already know about it, acetylcholine. See? One size fits all. I'm ecstatic about that. Better yet, all the post-ganglionic nerves of the parasympathetic system release one neurotransmitter. Guess what? Acetylcholine. Who knew? I mean, you can't beat that with a stick. And the other nerves in the sympathetic, save one component, release norepinephrine. And the other one, the one that doesn't release norepinephrine, you're right, releases acetylcholine. What a country. And you thought you had to do a lot of memorization. No. But wait, there's more. Buy now, and we'll send you 3 pillows. Buy now, we'll send you a sheet. Buy now. It's the old routine. Got no credit? We don't care. Can't afford to pay us? We don't care. Not going to pay us? Then we care. The original Tonight Show, prior to, not the original, but the most popular evolvement of the Tonight Show was a guy named Johnny Carson. Okay, and they're hysterical. That was from a thing that he did called, he played a character named Art Fern doing Tea Time Movie. And it was very clever the way he did it. But I move on. So here we are. In the somatic nervous system, the cell body's in the central nervous system, and you have a thick myelinated group A fast axon going all the way to the spinal and cranial nerves to skeletal muscle. In the autonomic, 2 nerve chains, preganglionic cell body in the central, thin, lightly myelinated preganglionic fibers to a ganglion, and then the ganglion outside by definition of the central nervous system, in an autonomic ganglion with non-myelinated postganglionic axon that extends. So it ain't fast. We say a mile neighborhood. It ain't quick. So you can see that. Somatic nervous system acetylcholine, preganglionic acetylcholine, postganglionic norepinephrine or acetylcholine, and it can be stimulatory or inhibitory depending on, again, the receptor. So that's always the hidden tail that's there. It relies on higher brain centers, coordinating them. This is when sort of the linchpin for a lot of this is the hypothalamus. That's the part of the brain where the blood-brain barrier is weakest. And that's where we analyze chemicals in the bloodstream, calcium levels, for instance, okay? Blood pressure. We're able to discern with chemical levels or mechanical levels and signal this system. Nearly, not all, but most spinal nerves and quite a few cranial nerves have both somatic and autonomic fires. You might remember, for those that weren't with us, and I think I did it again when we were in lab earlier, when we did a quick review, as I recall, of the cranial nerves. There are 4 cranial nerves that have parasympathetic. None have sympathetic components. 3, 7, 9, and 10. 10 being by far and away the most important. The others are less so. Not unimportant, but less so. This parasympathetic division is often called the cranio, for those 4 nerves, sacral division, because it plays a pivotal role in reproductive function. So craniosacral for parasympathetic. We call the other one the sympathetic thoracolumbar or thoracodorsal. And so it has thoracic and lumbar nerves as part of it. So cervical nerves are not coming to the party in this particular one. So active muscles, more oxygen and glucose to the autonomic nervous system, speeds up the heart rate, opens airways, increases blood supply to the aforementioned, to the heart and to skeletal muscle. This is a pretty good construct that you will see. So there you can see a multipolar nerve with a lot of myelination, releasing acetylcholine at a neuromuscular junction. It's always stimulatory. Here, you can see the 2-nerve chain, not terribly fast, lightly myelinated in the sympathetic system, either going to a sympathetic ganglia or to a unique sympathetic ganglia nestled in the inner core of the adrenal gland. The adrenal gland has 2 parts: the adrenal cortex, which releases what are called corticosteroids, which is only a part of the endocrine system, and the medulla, and probably the adrenal medulla is nothing more than a ganglia for the sympathetic nervous system that happens to be located in an unusual place, sort of a misplaced sympathetic ganglia. And what it does, it releases directly into the bloodstream, not just norepinephrine, but also epinephrine. And that, when that idiot cuts you off, why you're perspiring for a while, why it takes you a while to come down, while your heart rate is elevated, while your blood pressure, while you're somewhat distressed for a period of time. I would have said pissed off, but I didn't want to say that. That would be wrong. Remarkably upset, angry, disconcerted. Flabbergasted is a good word. Off kilter. Or
Distraught.
What?
Distraught.
Distraught is a good word. Not despondent, because that would be no hope for return. Distraught is a good word. If I had a disproportionate response to a disturbing. The best comedian ever for language, the late George Carlin. You'll find all of his routines. They are hysterical. He did an extremely funny one, just reading that, the thing you get in the airplane, where the safety features, and he starts reading it. It's hysterical. Should you need oxygen, bend over, put your head firmly between your thighs, and kiss your ass goodbye. Just saying. You have flotation things under your seat. Not for me, they won't. I'm in trouble. So you can see that is, as you can see, the sympathetic. The parasympathetic is interesting. In general, the sympathetic has short, this is important, preganglionic and long postganglionic fibers, probably with the exception of the one in the adrenal medulla. In general, the parasympathetic has very long preganglionic and comparatively short postganglionic fibers. So that's another little nugget that's part of it. Parasympathetic, body energy is as low as possible. I love that. Even while carrying out maintenance, and that's typically when you're sitting there, digestion, diuresis, defecation. That's when you're sitting around doing nothing. That's when your body is busy taking care of those problems. So they call it the rest and digest system. Okay, any of those types of things. Those rates are relatively low. Gastrointestinal and genitourinary is low. Your pupils are constricted. That's the big thing. And so what you're going to see is the pupils are constricted, the lens, close vision, because generally that's what you're doing. You're doing typically close work. In that context, you're going to see some terms. Okay. When we have medications that act and do the same effect as the parasympathetic, we call them parasympathomimetic. And when they opposite, parasympatholytic. By the same token, we have things that are sympathomimetic and sympatholytic. So if you know somebody who is, like you, if somebody who has taken an amphetamine to stay awake, ready for a test, that's a sympathomimetic agent. So somebody who goes to a party and takes ecstasy, that's a hallucinogenic agent that is in that category of sympathomimetics. It's an amphetamine-like substances. So one of the ways we tell somebody ODs with that is their pupils are not constricted, they're widely dilated. But on the other hand, narcotic overdoses generally assume pupils are constricted. Even if the person's coming.
Like, why are my eyes always huge?
Always what?
Like, my eyes are always huge. Like, no matter
I don't have an answer, honestly. I think some people it just to do with presets. It's like I said, you can't, when you deal with the body, you can't pay a hard and fast and steady rule. So some people, it's just, that's whatever your preset is, whatever your normal is. I've had people where I've injected local anesthetic and it's had absolutely no effect. They're refractory. There's no explanation. Scientifically, it should work, but so I mean, sometimes it's these are the kinds of things that you run into. So I used to say on a great show called Kung Fu, always expect the unexpected. Grasshopper. No context for that. Okay. Pupils constricted, lens accommodated for close, and the opposite, fight or flight. Mobilizing the body. All of those things. Emergencies, you go to the gym and work out. You go to the fight or flight. Embarrassment also, interestingly, heart rate, dry mouth, because it dries secretions, so it increases respiration. You perspire, but it's cold. The blood flow isn't there, but you're accelerating the perspiration basically to evaporate as a cooling mechanism. And the pupils are dilated. And as you can see, this is what it does. Blood to skeletal muscles in the heart, dilates the bronchioles, liver releases glucose. And so that's the whole idea. Parasympathetic craniosacral, sympathetic thoracolumbar, some people say thoracodorsal, and those are its origins that are there. Parasympathetics long pre, short post, sympathetic the opposite. Parasympathetic ganglia are near the target, near the heart, near the stomach. Sympathetic, very close. The sympathetic chain is, you'll see it, very, very close to the spinal cord. And I think we should stop here because how much can you listen to me talk? Don't start. Me. We'll pick it up with the parasympathetic on Wednesday. I'll see if I can get, if I don't have to buy another one of these, I'm sure I can get it. I do wear